Hey, everybody. Welcome to Adventures in Machine Learning podcast. I'm Ben Wilson, filling in for Charles this week. And on the panel this week, we're talking with Mark Ryan, who has written a book that was published back in December about using tabular data on deep learning systems to solve problems. And he's also got a new series that was released in April that is sort of a code example walkthrough that's being hosted by Manning. So, Mark, welcome to the show.
Thanks so much, Ben. It's great to be back. I had a chance to be on the show last year, so it's a real treat to be back again. Thank you very much.
Yeah, this is great.
When I went freelance, I was still only a few years into my development career. My first contract, I was paid $60 an hour. Due to feedback from my friends, I raised it to $120 an hour on the next contract. And due to the podcasts I was involved in and the screencasts I had made in the past, I started getting calls from people I'd never even heard of who wanted me to do development work for them because I had done that kind of work or talked about or demonstrated that kind of work in the videos and podcasts that I was making. Within a year, I was able to more than double my freelancing rates, and I had more work than I could handle. If you're thinking about freelancing or have a profitable but not busy or fulfilling freelance practice, let me show you how to do it in my Dev Heroes Accelerator. Dev Heroes aren't just people who devs admire, they're also people who deliver for clients who know, like, and trust them. Let me help you double your income and fill your slowdowns. You can learn more at devheroesaccelerator.com.
So before we started kicking stuff off, we were chatting a little bit before the podcast started about some of the controversy that people have when they start talking about utilizing deep learning for tabular data. And in academia, I've seen some of these discussions that people have had about we should never use deep learning for this use case or this other system is more appropriate. I just want to get your thoughts on how you see that argument playing out.
Well, I think what's happened for some other kinds of data, for image data, for audio data, for NLP, deep learning has really demonstrated itself to be streets ahead for a lot of application. So it's just the evidence is there to say you really would using what you would have used back in the 2000s just doesn't make sense for dealing with image data to a large extent, because the results with deep learning they're so impressive. They really are amazing. And then for NLP with transformer-based language models over the last 3 or 4 years, you've seen really amazing results there as well. So I think there's some controversy maybe about some edge cases. Nobody would argue that there are solid, incontrovertible use cases for deep learning for those kinds of data sets, just because the evidence is there. And partially because of the nature of the data sets, people can have a Kaggle competition. So that's the market speaking. If somebody is showing that success in Kaggle, then that really shows something. We have data sets that are open or public, people exercising them in that kind of way, they can publish, and the publication of academic papers on these data sets, it kind of sets a baseline. With tabular data, a couple of things. One is that the evidence, and there have been some publications say of really good results with tabular data with deep learning, but not the same kind of mic drop moment that we've seen with NLP and image data. And a lot of the work that's being done is being done behind the firewall. It's not public data sets. It's not something that can be shared in an academic setting or would necessarily be amenable to a Kaggle competition, because it's people solving real world problems with real world data, trying to keep businesses going. So what that means is there are certain people who are skeptical, and they'll point to Kaggle and say, look, if you look at competitions on Kaggle involving tabular data sets, XGBoost or its siblings have been much more successful than deep learning. Therefore, deep learning is not very good for tabular data. Case closed. So what I try to argue in the book is not to say that deep learning is appropriate for every kind of tabular data set, every kind of tabular problem, but to keep an open mind about it. And that there are applications where tabular data could lend itself to solutions through deep learning. And I'd say, with the publication of the Spirit paper this summer and further work on Tabunet, there's gathering evidence that deep learning is well worth considering as an option for tabular data. Not to say in every case it'd be better than XGBoost and its relatives, but it should be considered. And what we'll see, it's fairly predictable. If somebody posts something on Twitter to say, I've got this result with tabular data on deep learning, you can set your watch at 5, 4, 3, 2, 1. Somebody will pop up and say, yeah, well, XGBoost is better. So it's, I think to a certain extent, maybe both right. There's room for both, but people do get fairly didactic about it. I also think from the point of view of people who are proponents of XGBoost, they'll say, well, why would you want something that's more complicated? And I've seen this in the book. I do a side-by-side comparison of XGBoost and the deep learning approach for the data set that the major code example in the book is covering. And XGBoost, in terms of performance, out of the box is a little bit better. Not hugely better, but a little bit better. So I get it. And the other thing is, it was fairly straightforward to get to adapt the code to use XGBoost. Wasn't a whole lot of work. So I can see that. You say, well, keep it simple. And if there's a simpler approach to something, then use that as opposed to something that's more complex. But I think just being closed-minded to trying deep learning, to have saying maybe deep learning might be more amenable for certain tabular data sets, and encouraging research in that area. I think there'll be benefits there. I've seen some arguments to say this, it's really more like the nature of the data, and this is something that's getting frankly beyond my skill set in terms of saying that in terms of the linear algebra characterization of what the manifold looks like for image data or for audio data for NLP is very different than what manifold would look like for tabular data, and therefore the magic you get from deep learning for the kind of data sets I mentioned first just isn't there for tabular data. And if nothing else, the success of deep learning has been empirical. That is, it's been successful because people have demonstrated its success. And I'd be skeptical about a theoretical saying, well, it's not going to work because there's this theoretical contra to it. I'd be skeptical about that because many times people would have given up on deep learning if they had stuck to what the theoretical thoughts were at the time.
Yeah, you bring up an important point about it might not be the best solution for everything. And I 100% agree. It is not.
Yeah.
Can confirm from personal experience, but it's important not to set it aside and say, well, I read this paper last year that somebody at this vaunted educational institution, they did a bake-off on this clean open source data set, and it shows that CatBoost and LightGBM and XGBoost all outperform a standard random forest or an ensemble of trees of some other flavor. And we also tried TensorFlow. Well, that could make sense for that particular data set because generally you have extremely high positive correlations of coefficients associated with those features and the target that you're trying to optimize to. So it's trivial for a tree-based system on these open source data sets. Everything on Kaggle is like that. They're very clean. They're very predictable. The reason they're on Kaggle is to help people learn data science and machine learning so that they can get better, and maybe land a job eventually. But as you know, as you've already mentioned, real world data is never like that. There's a lot of variance associated with even something over a temporal space. Checking one feature over time, it's not always stationary. So there's complications associated with real world data that sometimes, something like XGBoost, for instance, can struggle with. The way that you get away from that is either passive or active retraining constantly. So you have to schedule this thing to, I'm going to retrain it every 3 days or once a week. And I'm going to validate that against my new feed prediction data and make sure that I'm performing as well as my previous production deployment. Whereas if you have something that has a high volatility associated with the underlying concepts of that feature, so your drift magnitude is very high, I've personally seen and worked with customers where it doesn't make sense to use those traditional ML packages. It makes more sense to use TensorFlow or, Keras wrapped TensorFlow and say, I don't need full model explainability here. I need high accuracy because this is running a part of the business and it needs to adapt to changes that we can't really confine within the spaces of how an entropy calculation would happen for a tree to make decisions on. So yeah, you're preaching to the choir to me on this. I think it's really important. So when you're at your company and advising your teams and within your book, when you recommend somebody to start down a path, when they have tabular data and it's a new project, what do you recommend that people start to look at and test?
So I think if you have a tabular data set that is fairly simple, so even something simple as saying something, the table that has a very small number of columns, and maybe they're primarily continuous, there aren't categorical columns, then I'd say and also if the data set's relatively small, then I say starting with deep learning is probably not a good fit for that. Not a particularly profound statement, but it's worth stating as a starting point. You get larger data sets, so get to the tens of thousands, hundreds of thousands of records. You get a higher proportion of categorical columns. And then particularly if you have columns that are unstructured themselves. So columns, something that's fairly common is you'd have categorical columns, continuous columns, and then text columns that might, let's say, describe an article being sold by a retailer, and it's free-form text. And that's something where deep learning can really shine because you can deal with that particular column with layers that deal with NLP. And even it can be very simple NLP. It doesn't need to be anything that sophisticated. And you get a lot of signal out of that. And that's something it's possible to do with XGBoost. You can have something off to the side, but it's a much bigger pain in the neck to do that. So just for efficiency's sake, those kinds of data sets, I think, are well worth considering deep learning for. And then I say on the bigger picture, there's all kinds of intrinsic data. So we're talking now about we've got a problem, and then what's the right approach to take, deep learning or more traditional machine learning approach. I think there's also a missing piece in research on deep learning. Or if you look at people saying, well, what are the limiting factors? There's a lot of talk about, well, you don't have common sense. There's sort of the deep learning approach. You don't have rules. You don't have sort of go-fi kind of description of how the real world works. Then there's something that's missing there, something that's fundamentally flawed. So Walid Saba, who is a very strong proponent for go-fi, and he's been on Machine Learning Street Talk. It's okay to mention another podcast. He's been on there a number of times, and he's saying, look, deep learning is fundamentally flawed because it's missing this ability to have a structure of how the world works. And it seems to me that structure is intrinsic, in some ways is intrinsically represented in tabular data. So some of it is very simple, the catalogs that exist in relational databases. So you have all this metadata that's there in any relational database. You have metadata about what tables that describe the tables. So there's all of that already encoded information. And to me, it seems like you're trying to do NLP and you ignore Wikipedia. So you've got this huge set of data that's just kind of waiting to be exploited. It seems to me that ignoring the potential of tabular data, of deep learning with tabular data, means you're missing out on all of that intrinsic metadata that's been assembled over decades in relational databases. Now, how to tap into that, how to make that efficient, I think that's a bigger question. But I would love to see some academic research focused on how do we take advantage of this. It's there. If you find a way to tap it. And on that, I heard a discussion of a paper. This was trying to overcome some limitations of very large language models, so GPT-3 type models. And it was recommended a very simple approach. Say, just in Wikipedia, there's all kinds of tables. So these aren't relational databases. They're just data instantiated as tables. And the approach was turn those tables into sentences, into a text format. You can do that in a deterministic way, and then use that as part of the training for the language model. And they demonstrated in this use case, it wasn't a huge use case, that it had a non-trivial impact on the performance of the model. And that really excited me. I thought that's interesting. Now it's a little bit of saying, well, we've got this, we trained the model with freeform text. So let's just disassemble the tables into freeform text because that's what the model is expecting. But I thought it was a very elegant way to get some low-hanging fruit from tabular data. So that interested me. And I guess this is all just to say, I think it's not just that, a business is maybe missing out on the opportunity for deep learning. I think on the academic side, not taking tabular data seriously is limiting. There are research directions that I think could provide some real breakthroughs that to my mind, aren't being tapped right now.
Yeah, I agree. And on the note that you brought up about particularly categorical data or text data that you're putting into a model, I frequently see people take a data set, tabular data set, that most people's data lakes and data warehouses are tables, right? in a database. Yeah. And they're taking that to train a model, and they're trying to solve this problem for the business. And they have this key critical value in their feature data. And you look at it, it's a string. And the first thing that a data scientist does kind of look at that and say, all right, well, I'm going to index that. I'm going to map this to some sort of monotonically increasing ID associated with frequency counts of this value. And that's all well and good. If somebody's been a data scientist for a while, they'll realize, all right, after I index this, I need to one-hot encode this to put it into a linear model. Because if I leave it encoded, that linear model is going to treat that like an integer or a double or a float. And you will get not so good results on your model. And then the XGBoost crew comes in and says, hey, you know what? We don't need to do that. We can handle categorical data on our own, which is fine if it's nominal, right? If it's something that there is some ordering associated with that and the counts aren't that big. But what happens with a categorical data point when in your data set, your training data set that has 10 million rows, and the cardinality of that field is in the hundreds of thousands? Well, I mean, spoiler alert, XGBoost doesn't know how to handle that. It's going to try to split on conditions based on how that indexed value is looked at. It's going to do its differential entropy calculation. It's going to say, well, I see a difference here at index position number 27,322. That doesn't mean anything to that categorical data, the underlying data. So on deep learning with tabular data, I'd be interested to hear what your experiences are with that condition.
Right.
And then I can tell you what mine are.
So in the example in the book, they use embeddings for the categorical columns. And that was to sort of say, okay, we'll see how this works. And there's an experiment in the book describing what's the performance if we don't have embeddings for the categorical columns versus having them. And it does make a difference. So having that as part of just the structure, what you can get in Keras, maybe not for free, but pretty conveniently from a coding perspective for the categorical columns, it certainly improves the performance of the model. So I said that's something that's clear. And can you take advantage of embeddings in something that's rooted in XGBoost? Yes, you can. But then you've got this sidecar thing that you have to worry about and maintain. And you say, well, if there's benefit in doing that, you have to do the sidecar, then the simplicity selling point for XGBoost kind of goes away. If XGBoost can handle it out of the box and you don't need to have deep learning thingies off on the side, well, that's fine. But if you do to get reasonable results, and I say it's worth asking the question, maybe deep learning should be in the driver's seat.
I mean, it makes a simpler architecture because you're no longer having to glue these things together.
Exactly.
Your code becomes far more complex when you're doing that. It's more error prone when you have to do changes to it. So for the people that are curious and that are listening in that come from a non-deep learning background, what would you say is the best way to get started in exploring this? If they've never really, there's a lot of people out there that may have done work with CNNs or LSTMs. They're used to that time series data that's coming in or image data. But if they have no experience trying to get tabular data working through deep learning, where would you say, hey, here's the roadmap for you to actually build something?
So from a standing start, if you had asked me a year ago, I would have said, to start with Keras because you're starting with a framework that's at least fairly high level, and here are a bunch of steps you need to make this work in Keras, because Keras really provides no scaffolding for tabular data. It's sort of agnostic about whether you use it or not. You can certainly, there are existent proofs that you can use Keras to make deep learning models with tabular data, but you're on your own. You have to take care of the categorical columns. You have to worry about if Ohio is mapped to the numeric identifier 0 at training time, you have to worry to make sure at inference time it gets the same.
Mm-hmm.
And you have to maintain that and make sure that happens. So what I would say for somebody who is starting from ground zero with tabular data, I think FastAI honestly provides a really quick path to doing experiments with tabular data. And the reason is that FastAI treats tabular data along with image data, text data, recommender systems as a first-class citizen. So you've got structures within FastAI. You've got a model structure in FastAI specifically meant for tabular data. You have little rendering convenience functions for tabular data, decent examples and documentation for how to do a hello world example with tabular data. So for that initial for somebody who's coming from a different background, FastAI is really easy to get to that approach. And particularly somebody who's coming from a PyTorch background would find it particularly easy. So that's what I say. Keras is certainly it's possible. I think my book attempts to lead through that. But I'll be honest with you, fast AI makes it that you get a faster on ramp. And again, particularly for somebody who has a PyTorch background.
Nice. Yeah, that's good advice. So one of the things that I can't tell you, of course, which company I work with these projects, but I've been working with a customer who is doing, actually, they're referring to your book, and they're looking at a problem where the number of features is truly gigantic. Just the scope of this problem is extreme. And they're not interested in the actual prediction. In fact, they don't even use a prediction from this supervised learning technique. But one of the things that they've done is they're building an autoencoder effectively. So they're taking these actually millions of features that go into each tabular row of data and passing it into a model just so that they can take a pooling value to reduce the dimensionality of that massive input set. How often do you see people doing that with tabular data, or is this kind of fringe one-off thing?
I can certainly see situations. So I imagine, I don't get too much into the details of your client, but I imagine this would kind of manifest itself either as a very complex schema or tables with lots and lots and lots of columns.
Yes.
So I've seen some examples of very large, like complex tabular structures. But what you described, this isn't something I've heard of before. It's very interesting. It's sort of it's kind of like a bank shot to say the goal isn't to get a prediction, but to have something to have the way you described, like an autoencoder kind of setup. No, that's very interesting. I see how it would be useful, but no, I haven't heard of people doing that before. Now, that being said, part of the nature of the way that deep learning is being used with tabular data, this you and I both know, it's being used by large corporations on their data, on their crown jewels. So they're not necessarily going to be publishing papers about it or making submissions to NeurIPS to say, here's what we've done, because they can't talk about it. Or if they can say something about it, it ends up being very redacted because they can't share the data set. You can't have something that's reproducible. You go and spin up a Colab instance and redo it because the scale and the value of the data just doesn't make it possible. Which is to say, it may be that the situation you're describing is common, and the fact I haven't heard about it doesn't necessarily mean that there aren't other businesses that are trying to do the same thing.
Yeah, I actually have only seen one other company do anything like that because it's a very specific sort of domain. But there are other use cases that I've seen people getting clever with sort of traditional ML and saying, well, I don't store all of this data in my database because most data warehouses can't support millions of columns, but they do store it in a normalized format that they can then denormalize at inference time and training time. And that basis expansion, that pivoting that happens creates potentially hundreds of thousands of features. And the curse of dimensionality that happens with traditional ML renders a lot of that just untenable. So if you have 100,000 columns, how many rows of data do you need? 10 trillion, 50 trillion? Yeah. Nobody's going to have a training data set that's going to do that. And if they do, they're on my company's platform using Apache Spark and probably Spark ML to deal with that. But even then, there's not really a benefit to the cost associated with that. So it's historically people use a dimensionality reduction scheme of like PCA and say, hey, we can't process this many features. We want to reduce 100,000 down into maybe 100. But at that point, it destroys information. You're losing all sorts of context about what the nuances are of that data. But with deep learning, we're not doing that. So what are your thoughts on that trade-off with the ability to handle all of that nuance to the data without having to destroy information, but the trade-off of that with explainability?
Hey folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
I think it depends on the application. So in my current job, which is in a regulated industry in auto insurance, explainability is everything, because every time a new model is released, we need to literally go to the regulator in Canada, the provincial regulator, and say, this is what the model did last time. This is what it's doing now. So there's been, for good reason, because of that, the team has been fairly allergic to applying deep learning specifically to auto insurance problems, because there are concerns about explainability. So I think that being completely black and white about it doesn't make a whole lot of sense, because I think there are cases where if we could set a baseline with the regulator and say, this is where we're starting from, and provide some more, maybe not be able to have explainability the way we'd have with traditional ML model, but some sort of statement in terms of the features that are making a difference, that it could be, you could get across the finish line. And then there are lots of applications where there isn't a regulator involved, or explainability. It may have an internal reason, but if the results are there, if you can demonstrate the results, demonstrate them consistently, empirically, then that may be enough to make the business case. And then the other side of it is, what I've seen happen is when you have a human being involved in feature engineering and trying to sort of second guess how things go, you can end up having, you need such a large team of data scientists trying to do the care and feeding for that kind of a setup, that it's not tenable, or it becomes calcified, because it just, you say, okay, we cannot make this any better, because we can't keep adding people to it. Whereas with deep learning, there's at least the potential to let the algorithm do the heavy lifting. I'm simplifying there, but not having a human being sort of trying to second guess and say, well, how do we finesse this? And you think about vision data. If in 2009 the same approach that was being applied there kept being applied today, it would be better. It would be better, but there would be tons of people just trying to squeeze out something that was half as good, as quarter as good as deep learning, where you say, okay, let the code self-gen.
Using the Python pillow package to do geometric relations and shape detection in images. Been there, done that. Don't ever want to go back. That code sucks. But the explainability, one thing that I end up seeing I don't see it in highly regulated industries, that I think that's still lagging behind the rest of. I consider it in three pieces of what the ML community is in companies. You have the cutting edge startups that they're just kind of hoping nobody regulates them, but they're going at the speed of light. So they're testing all the new things as fast as they possibly can. And they're very agile because they don't have technical debt. They don't have a history of business requirements that they restrain what they can and can't do. And then you have the middle of the road companies that maybe they're established high-tech companies, but there's a lot of process that has been built into how they do things because they've made mistakes in the past and they've learned from them. And that's wise. If you're an established company, you should take things a little bit slower and more methodically, and making sure that you have all your ducks in a row.
The cost of mistakes is going to be higher. You have an established. You have clients. You have a reputation. So you screw up, the implication is going to be worse than a startup where give it a try.
You know the first names of all your clients in a startup. And then you have the regulated industry where government is involved in making sure that industry is dotting I's and crossing T's. And I think they lag a little bit behind that middle of the road because of the fact that you have laws on the books that are controlling how you do business. But what I'm starting to see is that some of the middle of the road companies that skew towards that regulated side, but aren't fully regulated, they're starting to get what the more startup focused people have been using for the last couple of years is stuff like kernel SHAP on deep learning, where they build this black box model and they're okay with, they don't have to know why all these weights were what they were. No human can understand that unless you have some sort of quantum computer embedded in your brain to understand how those things were calculated. But I've looked at them before and I'm like, I have no idea how that did that. The CNN, no idea, but it's cool. And you can simulate stuff with a model, but utilizing something like kernel SHAP, which it doesn't care what sort of model you're doing. It's just saying, here's my tabular data set and here's my model. Predict row 1 and then row 1 substituted with values from row 3 on its features. Calculate the difference between them for each feature and repeatedly do that. I've started seeing people do that with SHAP and producing these reports that they can send to business leaders at their company to say, we don't have full explainability, but we understand the impact that each of these features have to this model. And I was curious if you're seeing that in regulated industries starting at all with respect to deep learning.
So let's say you've seen some investigation of this, but there's in regulated industry that I'm aware of is auto insurance. It's still fairly conservative. So some research looking at something, is this something we could do in the future, but not something that's on the horizon immediately. And some of this, you mentioned the technical startups not having technical debt. So some of it as well is successful in auto insurance companies have made an investment in data science over the last decade. So they have incumbent bodies of code, and replacing that, sort of tearing that down, and the prospect of replacing something that's based on traditional machine learning with deep learning the business case needs to be pretty strong.
Right.
They look at the precedents. So Google throwing away what they had spent, I would imagine, tens of millions of dollars on with Google Translate, saying, okay, we're going to throw that all away and replace it with deep learning. Now that's the kind of company Google is, and have deep pockets, but they've been very successful with that approach. And I'd say for the auto insurance industry, there's maybe some hesitancy, want to see somebody be successful with it first before moving forward.
Yeah, that's the thing that I notice. The more companies that I interact with is the more conservative the company. Everybody's hoping that somebody else does it first, successfully, so that they can then get the justification to say,
you can point to them and say, we're going to fall behind if these guys are doing it now. So now we have to commit to it.
Yeah, and it's when I talk to tech people, when one of those events occurs in certain industries, the tech people at the other companies on that next call that we have, they're so excited. So like, oh, this company that is a major competitor of ours just released this massive report with this white paper that goes along with it. We're excited because now that means we have carte blanche to go and finally do that.
Yeah.
A lot of times, some of these teams have sub-teams within them in the data science groups. It's like a skunkworks project. A lot of the times that I've noticed, they already have stuff ready to go. They've already done the internal research.
Really, it's just kind of like pull the sheet off and, we just happen to have this. And,
yes. Yep. So it's interesting when you see stuff like that. And I'm curious what you think the future is going to hold for broader adoption of this tabular interface with deep learning. Do you think even in regulated industries, people are going to start doing stuff like that?
Yeah. So I think it is going to happen, and I think it's going to be inevitable. And ultimately, it'll be empirical. There'll be a demonstration that this is successful. And maybe it's not a perfect analogy. Look what's happening with autonomous vehicles. And there's regulations there, and there are people who say, no, it's decades out at best, because there's going to be regulation and the law, laws regulating vehicular traffic. And there are companies, and there's no guarantee they would succeed. So it's possible that Tesla's approach to self-driving will crash and burn. I don't think that's the case. I think it will be successful, but that's we don't know yet. It hasn't been empirically proved. But I think if Tesla is successful, they're just showing it and say, look, we've got millions of miles of demonstration that people are, there are people who are alive today because of self-driving. That is going to create pressure on the regulatory environment. So it'll be less sort of arguing with the regulators. It'll be more empirical proof that the approach is better in the case of autonomous driving. So for where things will stand in regulated industries for using deep learning with tabular data, I think it's probably going to be something similar, that there'll be empirical evidence of the viability of deep learning, and combining with what you described to be able to say, well, we can't categorically say the impact of every single feature, but we can say which ones are most important. That's going to move things along. And the opportunity cost of not taking advantage of deep learning for some data sets will be so high that that's going to create pressure to apply deep learning. Now, it may take a long time. And this question about people not knowing where the successes are because it's happening behind the firewall, I think that's that problem isn't going to, it's not going to go away.
I like that analogy you used about self-driving cars, because it always triggers in me wondering why people have such a resistance to that. And I notice it in the zeitgeist of people saying, Well, we don't want any accidents to ever happen with autonomous vehicles. And then logically you start thinking like, well, why don't we have that same requirement for humans? Right. So why do we have expectations that, yeah, somebody can smash into me with their car and that's fine. But if a computer does it, then that's definitely not okay. I'm not saying, hey, I want autonomous vehicles to be smashing into my car when I'm on the road, but there's a different burden when you're talking about like blaming humanity versus blaming something that humanity creates.
Yes.
And I've seen this in my career for data science as well. A couple of times I've come into companies as the first data scientist and had to build out a team. And I see that same resistance when it's a prior art that's existing. There's a team doing some task. Their management says, we want to automate this because it's not that we want to lay these people off. We'd rather have them do something more creative that humans are really good at, that a computer can't. And we think you can automate this, which is a perfect example for data science use cases and ML. I think that's why it exists in a lot of companies, to free the human mind. But they don't usually like it at first. The humans that are doing the job attack the ML solution almost instinctively because it is this automaton. This is this unknowable process to them. And it almost gets emotional for a lot of people from my experience. So what I would expect to see is this same battle to happen with tabular deep learning approaches for all of the people that have been using traditional ML, and how much of an improvement to process, and also how long do you think it's going to be for people to shift their paradigm to adopting something like that?
Yeah, there's certainly power in incumbency. If you have something that's working, then why mess with it? And what you describe in terms of group dynamics, people will tend to sort of say, there's going to be a change. Well, guess what? I have 5 reasons why this is going to fail. Mm-hmm. And we're not going to talk about the flaws in our current situation because it's there, it's up and running. So yeah, it's not perfect, but here are my 5 reasons why this new approach is going to fail. And my sense is people who are arguing right now for XGBoost, they're doing it in good faith. And they really do believe that the evidence they see is that XGBoost is the way to go with tabular data. And there hasn't been sufficient evidence on the side of deep learning that's broad enough to say we should have an open mind about deep learning across the board. And I think, I think there certainly is a population of data scientists who, for one reason or another, either because they didn't have this background or they're skeptical or they think deep learning is overhyped, they figure my career and my interest, I'm not going to bet it on deep learning because I think there's too much smoke and mirrors. It isn't tightly bound enough to theoretical underpinnings. It's too empirical. The bubble is going to burst eventually. So I don't want to really invest my emotional energy in it. And I'm going to be a skeptic. And there are places and organizations, and there are, that kind of pushback isn't a bad thing. There should be some challenging people over promising with deep learning. That certainly has happened. But I think data scientists who say that they're not going to have an open mind to deep learning in general, or they're not going to invest the time to at least get some basic understanding, I think they're cheating themselves. And I believe I don't know if it's going to be in 5 years or 3 years, but I believe that there will be a tipping and there will be a point at which deep learning is mainline orthodoxy for dealing with at least a large class of tabular data problems. I think it's empirically going to demonstrate what its benefits are. I think something would help that I mentioned before, having more academic research aimed at what really getting the most out of what tabular data sets can provide. If that starts to get some traction, then that will help as well.
Hey, folks, I don't know if you've noticed, but I've been working a lot on figuring out how to help people become the most valuable developers on their teams or becoming the top 5% of developers in the field. If you're looking to level up, figure out how to contribute more, get the career you want, get the career that you want that will support the lifestyle you want, then you should check out the Most Valuable Dev Summit. I've invited some of my friends across the community, people that you've heard of, people that have worked on systems that you use on a daily basis, people who have invented new ways of doing things over the years in programming, and I've asked them one question, and that question is, how do you become a top 5% developer? How do you become 1 in 20 of the best developers out there. And so we're going to go ahead and have that conversation with them in interviews on the Most Valuable Dev Summit. And you can find that at summit.mostvaluable.dev.
As well as, I kind of teed it up for you there, but you didn't even drop the name of your book and reference to your courses. But the reason we're talking.
That's right. You want to say yes. It'd be entirely up to me to make the difference. I'll be pivotal. Yeah. So my book, Deep Learning with Structured Data, which came out from Manning at the end of last year, it goes through a large scale code example of applying deep learning to tabular data. It also compares the results with XGBoost from end to end, from a very messy. So it's a real world data set that's extremely messy, going from that to a deployed model. So the whole life cycle. It's very simple, but it's the whole life cycle, and talking about the considerations, what the pros and cons are of applying deep learning to tabular data, and some of the assessment criteria. So that's the book. And then in April of this year, Manning released a series of live projects, which takes the same approach, but with a different data set. So the data set for the live projects is a data set of Airbnb listings in New York City. Mm-hmm. And the problem is predicting whether or not a listing is going to have a nightly cost that's above or below the average. So it goes through the same thing. The data set really isn't that messy. So that's, it's less time on the cleanup of the data set, but it does have more of a geospatial aspect. So it talks about, mapping visualizations for the data set, then creating the model, and then deploying it as well. So using similar coding approaches as what's in the book, but with a different data set and some different aspects to it. And that's a set of 3 live projects: cleaning up the data, preparing the data, creating and training the model, and deploying the model.
That live project use case is very prescient in many use cases that companies have that I deal with. And some people are pursuing that. Actually, they're taking tabular data that has geospatial information about it, and they're plugging in not just base TensorFlow, but they're doing graph embeddings of data within the actual weighted nodes, so that the model can start learning information about geographic relations between data. And that graph embedded deep learning framework, it's one of those sort of scary things when you see how accurate it can be when you just pass in the data as, I have lat-long coordinates, and those are just 2 features that are going in. And then building graph representations of how that correlates to other rows of data, other vectors that are being passed in. And all of a sudden you see the actual accuracy improvement over that base. It's pretty shocking. Computationally, it's pretty intensive, but from what I see and the results that some of my customers I've interacted with have gotten, I'm seeing that as kind of something that is the next generation of using that. And for those sorts of use cases where you're trying to figure out what is the optimal way to solve a traveling salesman problem, you can brute force your way through that. Put all the data in a graph. Good luck with your breadth first search and depth first search. Have fun. But it's computationally expensive. Whereas you can actually train tabular data connected to the graph embedding of those relations, and it just learns things that seem almost too good to be true, but it's some pretty interesting stuff.
That's I had not heard of that. That's very interesting.
But like you said, this stuff is firewalled. I wish there was a world in which we could live where companies were freely sharing information about how they're solving problems, because some of the most clever things that I've seen in my career has been because of some geniuses working at a company in a back room, figuring cool stuff out. Sometimes they're wrapping a framework around these open source frameworks that add so much new functionality, but their corporation doesn't allow them to contribute back to the open source because of intellectual property laws. And it's a shame.
So it becomes some kind of isolated evolutionary chain that it's on that island, it can grow, but the rest of the world doesn't get the benefit from the really sharp tusks and whatever the animal.
Yes.
There's, I think, part of it is an attitude. There's a guy called Luca Massaron who's done a couple of great videos on deep learning with tabular data and talking about it very practically, very meat and potatoes, how to do it. And he's found a way, and he's working on this stuff behind the firewall, so he can't share what he's doing exactly, but he's found a way to share some abstractions at least. So some of it may also be having corporate cultures that encourage people to share what they can. I think there's benefit there. People can be inspired a little bit. It's not the same thing as saying, well, here's the GitHub repo and here's the data set and go wild with it. But at least talking about some approaches is beneficial. Maybe we need a conference that's focused on deep learning with tabular data to get some like-minded folks together to talk about this. I don't think, as far as I know, there's nothing that exists right now. But listening to what Luca had done, I really thought, wow, he's doing some great stuff, and it would be fantastic to give him a chance to talk about it in a little bit more detail, not as a single, like a one spot on a conference about something else, but do a keynote, I think. And there are probably dozens of people like him doing work behind the firewall who'd have great things to share.
Yeah, definitely. Okay. Is there anything else you wanted to really pitch or talk about with regards to the live courses or the book?
I think that's the book goes through things in a fairly basic way, but it is end to end. One of the things I wanted to make sure is I find a bit frustrating about some of the descriptions of deep learning is they get to the, okay, here's the trained model and see you later, and never even go through any of the basics about now get this thing to the point where somebody can actually use it. So I encourage people to take a look at that. And then the live projects have the similar approach to the code, a different use set, and then it's really focused on the practical coding, going through that a little, and not really trying to make the case about using deep learning with structured data. And the final thing I'd say is one of the lessons I learned, Manning, back in the early 2020, they said, maybe we should call the book Deep Learning with Tabular Data. What do you think? And at the time I thought, nope, structured data is the incumbent. We're sticking with the incumbent. It's what we know. We've been doing this for a while. And they were right. So if I learned a lesson here, because people will see structured data and they'll say, well, JSON's structured and freeform text is structured and image data is structured. So that was a lesson learned. So the title is important. So if I had it to brand again, I'd call it deep learning with tabular data, because I think that gets to the heart of it.
Yep, I would agree. I mean, I took a look at it. I'm going to be reading it again in more depth, and because, like we've mentioned, with the use case applicability to a lot of these different ways of solving problems, ignoring this approach is, in my view, it's like walking into a construction site and building a house, and everybody else has a full tool belt. They've got screwdrivers, hammers, crowbars, and saws hanging from their belt. And if you ignore a potentially super useful tool that you can use to solve certain problems, it's like walking into that construction site without a hammer. Yeah. And it's framing day. XGBoost is now your crowbar that you're hammering nails in with. So I encourage everybody who's listening in, take a look at it, get a copy of the book, read through it. Mark's a fantastic writer. You'll really enjoy reading through it. And I'd just like to say, Mark, thanks. This is a fascinating talk. Had a really great time doing it. And just thanks for showing up and talking through it.
Well, thanks so much, Ben. It really enjoys me. And the experience you have and sharing a little bit of what you've seen as well has been really helpful for me. I've learned a lot from doing it. So thank you so much. Really appreciate it.
All right. Until next time, everybody, thanks a lot. This has been Ben.
And Mark.
All right. Take it easy.
Thanks a lot.
Okay.
Bye-bye.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.